Okay, so now we're going to address more of the math behind the vector. Now, we recollect that this electric field vector E, with the bar over the top, has an x, y, and z component, represented by unit vectors of I, j, and k, respectively, and the components of ex, ey, ez. Now, for simplicity's sake, we'll constrain the conversation just to a two-dimensional vector. So we'll neglect the ez component or the k hat component or the component of the electric field in the z direction. Now, alternatively, I mentioned, can also represent the electric field vector as so k times q over r squared times r hat. So here we're going to focus more about the unit vector r hat and explore why these are two equivalent forms for representing the electric field. Now, this is our electric field vector E, this is our electric field vector E as well, so they must be the same. So let's go ahead and equate them to each other. We see that k times q over r squared r hat is equal to E times r hat, where kq over r squared is equal to the magnitude of our electric field. Remember, this unit vector just indicates the direction of our electric field, whereas this entire coefficient indicates the electric field's magnitude. And this is why you hear the rule of thumb that the magnitude of a unit vector must equal 1 in order to not alter the magnitude. So let's go ahead and equate it to the other side. We see this is exi hat plus eyj hat. Okay, and now we want to go back to our picture, and we recognize that ex is equal to e cosine of theta, ey is equal to e sine of theta. This is what we see in this triangle over here. We discussed this before. So now, taking that into mind, let's plug it in here. And what are we going to get? Well, we see that er hat is equal to e cosine theta I hat plus e sine theta j hat. Now we see that the magnitude of the electric field, which is E, is common in all of these terms, so they're all going to cancel each other out. Now we see something interesting. We see r hat is equal to cosine theta I hat plus sine theta j hat. So our unit vector dons this form, and as I said prior, a unit vector must have the magnitude of 1, which we say the vector is unity. It's another term you'll hear to describe that the magnitude of a unit vector is 1. Another way to express this as the dot product of a unit vector unto itself square root is equal to 1, or the square root of 1 is just 1, so just as well the dot product of a unit vector unto itself is equal to 1. So now let's represent this in matrix notation. So we see that we have cosine theta here, sine theta here, where the first element corresponds to the I hat component or the x component. The second element under sine theta corresponds to the j hat component or the y component. So let's take this dot product unto itself. So r dot r hat is equal to cosine theta sine theta dotted unto itself. And we see we get cosine theta squared plus sine theta squared is equal to 1. Aha, this is identity from trigonometry. Hence, every unit vector is equal to 1. So, here, cosine theta and sine theta here, their main purpose is to indicate the direction of the electric field in our picture over here. So I hope that makes sense and you see that connection